Hey everyone, welcome. In this video, we're starting an amazing journey, building a convolutional neural network completely from scratch, using only C++ standard libraries. To begin this series, we're going to build one of the most important core components in deep learning, our own tensor class, entirely from scratch. A tensor is basically how deep learning models store data, images, feature maps, weights. Everything inside the network is stored as tensors. In our case, we'll store data using the NCHW format. Don't worry if this sounds new. We're going to build everything step by step and make it very clear and practical. Okay, let's get started. Here, create a file and name it tensor.hpp. The first thing we write is hash pragma once. This makes sure this file is only included once during compilation. Now I include the libraries we need. Hash include vector. We use vector to store our tensor data in a dynamic contiguous memory array. And hash include array. To return the tensor shape, hash include algorithm. For utility functions like filling arrays or finding minimum and maximum values, hash include random. For weight initialization, hash include cmath. For math functions, hash include assert. Assert helps us catch bugs early by checking conditions at runtime. And we include cstd_def to use types like size_t, which is commonly used for indexing and sizes. And we create the tensor class. Now I define the tensor shape. Int n equals 0, this is batch size. Int c equals 0, this is channels. Int h for height equals 0, and int w for width equals 0. Next, I create std vector float data. We store all tensor elements in a single flat vector. This makes access faster, keeps memory usage efficient, and follows the same approach used in real deep learning frameworks. Then, the default constructor. This allows us to create an empty tensor. Next, we create the constructor to initialize the tensor with a specific shape. By marking our constructor explicit, we make sure a tensor is only created when we clearly call it like this. We use static _cast to convert into size_t because size_t is the type C++ expects for sizes and indexing. This prevents overflow when multiplying large numbers, like the total number of elements in a big tensor. Next, I want to create a constructor to initialize a tensor from existing data. Here, the and or reference means we're taking the vector by our value reference, so we can move it instead of copying. This is faster and avoids extra memory use. Let's initialize the shape variables and move the data into our tensor. Moving transfers ownership of the vector without copying all the elements. Very efficient for large tensors like MNIST images. Then we calculate the expected number of elements by multiplying all dimensions. Finally, we use assert to make sure the data size matches the shape. If they don't match, the program stops here with an error. Next, we add a few helper methods. Here's the first one. It returns the total number of elements in the tensor. Here, no discard warns us if we call this function but ignore its return value. it helps catch mistakes early. And const means this function doesn't change the tensor, so it's safe to call on read-only tensors. And noExcept tells the compiler this function won't throw any exceptions. Next, we add a helper to return the shape of the tensor. And next helper checks if the tensor is empty. Then we add an operator to access a tensor element by its indices. Inside the function, we use assert to make sure the indices are valid. Finally, we return a reference to the element in the flat data vector at the correct position. The index function, which we'll create in the private section soon, calculates the position in memory for these 4 dimensions, keeping access fast and efficient. Next, we create a read-only version of our element access operator. This works the same as the previous operator, but it's marked const, which means it doesn't allow modifying the tensor data. It's used when the tensor itself is const or when we only want to read values. Next, we add direct access to the flat storage using square brackets. Then we check that the index is inside the valid range. Finally, we return the elements stored at the position I inside the flat data vector. Next, we create a read-only version of the square bracket operator. What else do we need? Well, let's implement a method to reset all tensor values to 0. It's also useful to have a method to fill the tensor with a specific value. Next, I'm going to create a method to fill the tensor with random values. This method fills the tensor with random numbers between minus range and plus range. Then we create a random number generator. Here, static means it's created only once and reused every time we call this function, which is faster. std_random_device sees the generator with a random value from your system, so each run produces different values. And we define a uniform distribution, so all numbers in this range have equal probability of being generated. Finally, we loop through every tensor element and assign it a random value generated from our distribution. Now, I want to define a method for initializing our weights. We use this because proper initialization helps the network train faster and avoid problems like vanishing or exploding gradients. In this project, we use the ReLU activation function, and heat initialization is recommended for layers that use ReLU. Let's go ahead and define it. Here, we calculate the standard deviation for heat initialization. Next, we set up a random number generator. Now we define a normal distribution with mean 0.0 and the standard deviation we just calculated. Finally, we fill each tensor element with a random value drawn from this distribution. And let's create the index method. This method converts 4D coordinates, batch, channel, row, and column into a single index for our flat 1D vector that stores all the data. This method is private, so private, and here's the method. And inside the function, we use a formula to convert our 4D position into a single number. The formula looks like this. At first, this might look complicated, but it's actually just moving step by step through memory. Think of it like this. Our tensor is stored as one long line of numbers. So to reach one specific value, first batch number times C. This jumps over all channels from the previous batches. Then we add the channel, batch number times C plus channel. Now we are at the correct batch and channel. Next, we scale by height. This jumps over all rows from previous channels. Then we add the row. Now we are at the correct row. And next we scale it by width. This jumps over all columns from previous rows. And finally, we add the column. Now we are at the exact element in memory. So in simple terms, we're just flattening a 4D position into a 1D memory position while keeping the NCHW order correct. And that's it for our 4D tensor class. Now you know how to store, access, and initialize tensors from scratch, all in pure C++. In the next video, we're going to take things further. We'll build our own image loader, decoding grayscale 28 by 28 JPEG images from scratch without using any external libraries. And this entire project is available on my GitHub. The link is in the description below. I'll see you in the next video.